Hello everyone. This is part 3 of section 14.6 directional derivatives. Last time we saw the how the gradient can be used to find a directional derivative, and so we saw an example of that, and now we're going to do a little bit more with the gradient. And you can see these examples. First example, the set of examples, the first two examples here, just asking to find the gradient at the given point. So just to reiterate the formula for the gradient, when you have a function of x and y, the gradient of a function is defined to be the partial of f with respect to x of the function times I, and then plus the partial of f with respect to y of the function times j. So all we need to do here is find a couple partials, plug in the point, and then we will have found the gradient at that point. So for this function, we'll have to rewrite it as x squared plus y squared to the 1/2 for the partial of f with respect to x. We'll have to use the general power, chain, u to the n, whatever you want to call it. Swing down the 1/2, same quantity, x squared plus y squared, power 1 less, negative 1/2, and then don't forget the derivative of the inside. Now it's with respect to x, so y is a constant. Derivative of x squared is 2x, and derivative of y squared would be 0 because it's constant. So then the partial with respect to x is 2's cancel, we get x, and then let's swing this quantity, x squared plus y squared, to the denominator, to the positive 1/2. And so now evaluating that at the point 3, 4, x is 3, y is 4, so 3 over 3 squared plus 4 squared to the 1/2, and that's 3 over, this will give us 25 to the 1/2, which is 5. And then we'll do the same thing for f, the partial with respect to y. Okay, and again, general power, chain rule, bring down the 1/2, same function, x squared plus y squared, power 1 less, negative 1/2, derivative of what's inside. Now x is a constant, so the derivative of x squared is 0, and the derivative of y squared is 2y. So then we'll rewrite this, the 2's cancel again, y over, and then bring that quantity to the denominator to the positive 1/2, evaluate that at the point 3, 4. So now y is 4, x is 3, and we get some f sub y. Partial with respect to y at that point is going to be 4/5. Okay, so now we just substitute into our formula for the gradient of f of x, y, and I guess we're at the point 3, 4. So it's just going to be f sub x at that point was 3/5 times I, and then plus f sub y was 4/5 times j. Right, so that's all there is to it. Here's another example, just basically an extension of the concept to a function of x, y, and z. So the formula for the gradient here is the partial of f with respect to x. Let me just write it this way without the functional notation. Times I plus partial of y partial of f with respect to y times j, and the partial of f with respect to z times k. And you can use the functional notation if you want, but I think we all know what it means, and we evaluated at the point and so on. Okay, so we'll need the partials, all three of them this time. F sub x, y and z are constants, is just 2x. Evaluate that. At the point 2, 1, 0, so that's 2 times 2, or 4. Partial with respect to y, x and z are constants, so x squared goes to 0. With respect to y, z is a constant, derivative will be negative 3z. And then z squared is a constant, or z cubed is a constant, excuse me, so its derivative is 0. So then the partial with respect to y at that point, 2, 1, 0, would be negative 3 times z is 0, which is 0. And then finally, partial with respect to z, x and y are constants, derivative of x squared is 0. Here, y is a constant, derivative negative 3z is negative 3, so negative 3y, and then plus the derivative of z cubed, 3z squared. And so, evaluate that. At the point 2, 1, 0, so negative 3, y is 1, plus 2, z is 0, so that gives us negative 3. So therefore, our gradient of f at the point 2, 1, 0 is going to be f sub x for evaluated at that point times I plus f sub y 0 times j plus f sub z negative 3, so let's just say negative minus 3 times k. And so I'll just call it 4i minus 3k. Okay, now if we look at some level curves, we talked about these in the past, and for this particular function, let's say to let z equaling 1, so z is f of x, y, remember. So if 1 equals 2x plus 3y, then we'll solve this for y, so 3y would be 2x minus 1, and y would be 2/3 x minus 1/3. So if we draw the level curves, let's say off to the side here in the xy plane, I'll make this 1, and actually I'll make that 1/3. And this is a this would be a negative 1/3 here, and that's what we're passing through. And then the slope is 2/3. So oh, made a mistake, sorry. This would be a negative 3y, which would make that a negative equaling 2x minus 1, and then when we divide by the negative 3, we get negative 2/3 x plus 1/3. Okay, so my mistake. Alright, so I don't need the negative 1/3. Just get rid of that. And it passes through 1/3 with the slope of negative 2. So from there, say down to over 3, I don't know, maybe here, it's just a straight line. And then if we let z equal 2, we get 2 equals 2x plus 3y. Guess the same thing, minus 3y equals 2x minus 2, so y is negative 2/3 x plus 2/3. So it's the same type of line, parallel, but going through 2/3. So y is 2/3 and 0. So notice that the slopes for each of these are negative 2/3. And if we look at the gradient, remember it's f sub xi plus f sub yj. We can do that easily here. F sub x is 2, so 2i, and f sub y is 3, so plus 3j. The slope of this is 3/2 y over x, change in y over the change in x. So note that these are negative reciprocals, indicating that they're perpendicular. And so, a little note here, gradients are normal to level curves, normal or perpendicular. Okay, so these are really, the graphs of these are really just parallel planes, because we're in 3 dimensions. Okay, and then we get to the concept here, not perp. Draw a figure, and let's consider a figure, let's say that's a like a paraboloid. So I have a little circular base, a little hidden backside. Let's say it comes up and it's like a paraboloid. And we'll pick a point in the xy plane and consider its image on the function. So maybe right there where, this would be a trace of the function. So that's the point, x sub 0, y sub 0 if you wish. But then this is the z value. What we want is the maximum or minimum slope at that point. So we saw how we could, use the gradient in combination with to find the directional derivative in with respect to a particular unit vector. But here, what our interest is to find either the maximum slope or the maximum increase, or in the opposite direction, that would give us the maximum decrease. And that would correspond to the two vectors that are the gradients, okay, in the xy plane. So these notes, maybe let's mention them after we mention the theorem. It says if the gradient is 0 at p, then all directional derivatives at p are 0. That would be like you'd have this graph that we're talking about, and you're at the top. So no matter what direction you go in, any direction, all those slopes are going to be 0. So no matter what unit vector you choose, at the very top, the maximum, all the directional derivatives are going to be 0. But then if it's not 0, the largest directional derivative is going to be given by the magnitude of f, so that's what this represents. And the smallest, or the greatest in decrease, so this is a typo here, this should say decrease, is the opposite of the magnitude of the gradient. Okay? And so at that point, I think I'll cut it short and we'll come back and finally finish up with a part 4 bunch of examples.